All right. Hopefully, everybody had a good break. It's been a while, so just to bring us back up to speed here with a really quick review of what we were doing when we last left on Wednesday. Now, almost 2 weeks ago, is that we were working with comparators so that we could do searching and sorting without having to roll our own algorithms. We did this in C already using comparators. Remember, a comparator has to have this signature here. It returns an integer and it takes two const void pointers because it's generic, right? The types have been erased. And it returns something negative, right? If A comes before B. It returns 0 if it's equal to B, and it returns something positive if they're out of order, basically. And in Java, we also did comparators, but it's a little bit different because in Java, it's an object-oriented programming language. Now, what that means, as far as Java is concerned, is that everything in Java is a class or belongs to a class. So there are no functions just sitting out there, right? There's no comparator, my integer comparator that's just sitting out there. Instead, you actually need to define a class, a comparator, and then this is a parameterization. T would take place of if it's a comparator for integers, you replace it with an int or an integer, right? If it's a comparator for books, then you replace that with book. Whatever it's a comparator for. And it takes two elements, A and B, and it returns an integer here, exact same pattern. So we went through several examples here for of course, a list of integers, a comparator for integers, compare int here, that if it compares them in ascending order or non-decreasing order, so that if A is less than B, then they're in order and we return something negative, in this case just -1. Otherwise, if they're out of order, then we return 1, otherwise we return 0. We did the same thing for books, right? And the book comparator here was by title, right? Then I showed you the more modern way of doing this with using this method selector operator here. That if you wanted to create a comparator for books by author then by date, you could string these together. You could chain these together. In fact, this is what it's called. It's called chaining. Comparator comparing books get author. So you're comparing the author first, then comparing the book's published date, right? And why were we able to do this with the author and the published date? Because they were what is called naturally ordered, right? I showed you how to do this with the author class, but somebody already did this with the local date or local date time class. Of course, past to future, right? And the way that we did this was to make it comparable, right? And in the author class here, that means that you implements this comparable by author, right? Of course, you want author, you want apples to apples. You don't want the author class to be comparable by books, right? That's apples and oranges there. And the only difference is that you have this compare to method that takes another author. And then you do the exact same logic. You compare this author, right, inside the class to that author. So we look at the last name. If the last name is the same, then that would be 0. Smith and Smith. Then we look at the first name, right? And if the first name happens to be the same, then so be it. It just returns 0. That book written by Frank Herbert is the exact same book as that book by Frank Herbert, even if they're two distinct books. So if you want to, you can make it totally comparable by adding some sort of unique tiebreaker down here. With respect to a book, what would that be? This book and that book, they're never going to be the same, even if they have the same author, same first name, last name, same title, etc., etc. How are books uniquely distinguished in real life? By their ISBN, right? International, whatever it is, right? People, maybe by social security number or NUID if you're an NUID NU system, etc. Then we briefly used this to show you how to search. I screwed up and thought that there was a linear search, and there's not. Instead, I previewed what is called binary search. So that's where we'll pick it up now. The basic idea to this is that you assume that the array is sorted. You can then exploit that structure, right? The basic idea is if you want to search for K here, you look at the middle element, A sub M, okay? If that's the thing that you're looking for, then you're done. You got lucky. It was right in the first place that you checked for it. Otherwise, if the thing that you're searching for is less than the middle element, where would it be? In the left half. Right? If the key element that you're searching for is greater than that middle element, then where would it be? In the right half. In either case, guess what? You've cut the array in half. Right? You repeat this until you found the element that you're looking for, or the section that you're looking in gets so small, so small, so small that it ends up being empty, in which case you know there was no such element. So let's visualize that over here. I've already started by looking at the middle element right here, 12. Let's go ahead and say that we're going to search for, I don't know, 42. Say that the key element is equal to 42 here. It's right there. Now, normally, if I were to do this using linear search, what would I have to end up doing? I would have to go, well, that's not it, 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 not it. There, I found what I'm looking for. How many comparisons did I make there? 8, right? So how many comparisons can I get away with now by exploiting this sorted structure? All right. So I'm going to start, first of all, at these endpoints. This is my left index, and this is my right index. I'm giving you a hint as to how we're going to actually implement this. All right. Kind of similar to how we covered recursion, right? Keeping a track of a left index and a right index, and then you move them in on each other to see if it's a palindrome, right? From before the break. So we look at the middle element here. By the way, how did I get to the middle element 5 there? I've got 0, right, and 10. So 0 plus 10 divided by 2 gives me 5, right? Arbitrarily, if I just had left and right, how do I find the index in the middle of them? Left plus right divided by 2. Why is that? That's the average, right? Yeah, go ahead.
We're taking the average for, like, I guess, an index that has like an odd number of.
Correct. So what if?
You have to have linear truncation or something.
Yep. If and then we want that actually, right? Because if you ever, if suppose that it was like 11 divided by 2 instead of 10 divided by 2, right? Then it would be 5.5, but that's not an index. 5.5 is not an index. So what do? We rely on integer truncation just to go down 1, right? And that's what we'll be doing in both languages. In languages that don't have integer truncation, you do need to take the floor or the ceiling explicitly, right? Because those are not valid indices. So I'm going to look at the middle index here, 12. Is that the thing I'm looking for? No. So I'm going to note here that I made one comparison right here. Where do I go from there? The thing that I'm searching for, 42, is greater than 12. So do I need to bother looking at anything over here? Nope. So what am I going to do? I am going to update my left index to what? Oops, I don't want the entire thing. I just want this part. Come on. Nope, I'm going to end up having to move the entire thing. I should have wrote it further away from my image. There we go. Now I can move it. There. Where am I going to move it? 6. Why not 5? I already looked there, right? So I'm going to move it over here to 6. In either case, from either perspective here, I'm only looking at this section now of the array. Okay? So 6 plus 10 divided by 2, just taking the average is going to give me what? 8. And so my new middle index here is going to be this guy right here. Is that the thing I'm looking for? Nope. I've only made now 2 comparisons and I still haven't found it. But the thing I'm looking for, 42, is now less than this middle element a sub m right here. So where do I go searching now? Over here, right? And now my indices are 6 and 7. 6 plus 7, 13, divided by 2. Here's where integer truncation comes in. 13 divided by 2 is going to be 6.5, but truncated is going to end up being 6. Is that the thing I'm looking for? Nope. So I've made another comparison here, 3. And then on the next iteration, what do I end up doing? I end up moving this over to here, right? Except without the the hash mark there, right? And now I find what I'm looking for with this final comparison. And so how many comparisons did I make ultimately? Half as many on this small array right here, right? Now, I'm not going to get into the big old math here, but let's think about this. How many iterations would I end up doing for an unsuccessful search? Suppose that I was doing, say, 43 instead, right? I didn't find what I was looking for. L and R would end up being what? Here's L, here's R. They end up coming together and meeting, and they meet at one element, but that's not the thing I'm looking for. So what ends up happening? They go past each other, right? That's going to be an unsuccessful search when L ends up being over here and R ends up being over here. Let's think in the worst case scenario here. Let's think about the iterations. The first iteration. Let's think about the size of the array that we're searching. Now, the section of the array that we're searching for. We start off with n. And now let's keep track of the number of comparisons as well. Okay? So on the first iteration, I'm looking at n elements, and I make one comparison to cut it down in half. So that on the second iteration, how big is it now, roughly? Plus minus 1, don't worry about those details. Right? Now it's about half as big. I make one more comparison to cut it down again for the third iteration. How big is it now? N divided by 2 divided by 2. You tell me, math-wise, what is that? N divided by 4. All right? I cut it down again with one more iteration, 2, and now tell me what the pattern here is. If I cut it down one more time, it's going to be n divided by 8. Right? Dot, dot, dot. On the ith iteration, I've cut it down how much? 2 to the I, roughly, right? So it's off by 1 there, but it's technically minus 1, but I'm not going to worry about that, right? I'll just say about. There we go. Because if you want to, you can rename your iterations to be 0, 1, 2, dot, dot, dot. Right? You're just off by 1. And then it will work perfectly. Dot, dot, dot. We make one more iteration, dot, dot, dot. When do we stop? So, how big is the array when we stop and find what we're looking for at the last possible spot? So here's L and here's R. Coming in, we've met. How big is that array of one element? 1. Right? So 1. How many iterations was that? For what I gave that to me? Now here's where the math comes in. N divided by 2 to the I, when does that become 1? In other words, how many iterations do we have to cut n in half by in order to get down to just one element in the array? Well, now it's just algebra. You tell me. Solve for I. 2 to the I on the other side. Okay. How do I get rid of that 2 and isolate the I there? Log, but be careful, what kind of log? Base 2 of n. All self-respecting computer scientists always work in base 2 or base some power of 2. Why? Because of binary, right? We're not regular old humans that work in base 10. We're not mathematicians that work in base E, the natural log. We work in base 2. Okay? So anytime that you ever see log of n, implicitly what base is that? That's going to be 2. Doesn't really matter because you can change back and forth from one base system into any other base system by using the change of base formula. Right? Don't worry about it. Okay? So in other words, how many iterations did I end up going? In other words, I make one comparison for each iteration, and I make log base 2 of n comparisons. Do you remember the other search that we looked at? We hinted at what it was. It was kind of linear search. Right? Why was it linear search? If I'm looking at the size of the array as n and the number of comparisons, in other words, the amount of work that we end up doing, what does linear search look like? Something like that, right? In other words, it's going to be n, right? The identity function there. Now, even if you want to look at it on an average case, right, then you could cut that in half, right? Because you're not always going to get unlucky and have to look at the entire array and find out, oh, that it's not there, or that it's in the last place that you looked for it, right? Instead, you're going to maybe get array with only half as many comparisons on average. Does that really matter? What's the difference between those two functions? From a calc point of view, right? What function is this? It's a linear function. What kind of function is this? It's a linear function, just with a different coefficient. If I took the first derivative of this one, what would I get? 1. Its growth rate is constant. The first derivative is the growth rate of a function. If I took the first derivative of this, what would I get? 1/2. It's also constant. Now let's look at binary search. What does it look like? At least on the scale of this graph. Log. What does a log function look like? Yeah, it's going to be so... If I were to actually graph this on, say, Wolfram Alpha, you wouldn't even see it. Right? It's going to stay so low to 0 on this scale that, no, it's not even going to be measurable. Let's look at it from that perspective of a calc. This is a good calc question right here. What is the first derivative of log base 2? Does anybody know that off the top of their head? No. All right, but do you know what the first derivative of the natural log is? Yep, 1 over n. So pull out in your memory a change of base formula, right? And realize that the only difference here is going to be 1 over natural log of 2, which is a constant with an n out front. In other words, it's going to be some constant 1 over n. Right? In other words, it's the same thing. Now you tell me about the growth rate of a log function versus a linear function over here. Right? The growth rate, what's happening to it as n gets bigger and bigger and bigger, as the array size gets bigger and bigger and bigger? What's happening to the growth rate? It's getting smaller, smaller, and smaller. Right? It's not staying constant. It's getting smaller with respect to the input size, the array size. Let's look at it from one more perspective. Suppose that I have 1 trillion elements. In other words, n is equal to 1 trillion. Tell me how big that is. 10 to the 12th, right? Yeah, 12th. 10 to the 12th. Right. So what about linear search? You'd expect to make how many comparisons? If it's n divided by 2 on average. That's going to be what? 500 billion? Okay. But what about this binary search here, this binary search idea? You end up doing log of 10 to the 12th. All right. Log identities. What can I do to that 12? Where's it go? Out front. Log, and again, it's base 2 of 10. So log of base 2 of 10 is about, what, 3.3 something, something, something. This is definitely less than what? 40. All right? So, 500 billion operations versus 40 operations. Which one is better? It's orders of magnitude better to use binary search, this binary search idea, because you are cutting it in half every single time. Divide and conquer, right? You're dividing it in half, 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 until you get down to nothing. Yeah?
What's the point of using linear search?
If it's not, so what was the key word with respect to binary search? We assume that it is sorted. So if it's not sorted, can we use binary search? Nope. Right. But we could do what first? Sort it, right? And that's where we'll go next. But I did want to show you an implementation of binary search here. Usually the approaches are going to be divide and conquer and therefore recursive, right? But I'm not going to do recursion. I'm going to immediately jump to an implementation that doesn't do that. I'm going to do what I just presented to you. I'm going to keep track of a left index and a right index. So initially, where should I start each of these? If I'm searching an array of size n. So the left index is going to start all the way to the left, 0. The right index is going to start all the way to the right, and careful, -1. There we go. All right. Now I'm going to keep going until these two meet or they go past each other. So while, right, left index is less than or equal to the right index, I need to keep going. I've got this situation where I've got two fingers here. One of is over here and one is over here. In other words, the size of the array, the section of the array that I'm looking in is not empty yet. Okay? I need the middle index first. So middle index. How did I get that, by the way? How did I do it before? The average, right? Left index plus right index divided by 2. Relying on that integer truncation so that I don't have to take the floor. Now, crossing my fingers here. This is bad, right? If you want to know why doing this is bad, it's because it's overflow. Watch the videos for the full detail or read the chapter in the book for the common pitfalls. But basically, there's a better way of doing this. Take the left index plus the right index minus the left index divided by 2. And it's a little bit more complicated, but math-wise, it comes out to be the same thing, and it's not susceptible to overflow. Right? Imagine here that this is like 2 billion. 2 billion. You'll end up with what? 4 billion. Can you fit 4 billion into an integer? Nope. So it only manifests for very large arrays. Right? All right, so there's the middle index. I look at these three possibilities. If the middle index is the thing I'm looking for, right? If the array sub middle index is the thing I'm looking for, then I'm done. Let's return the middle index. I'm going to return the index at which I found it. Okay? Else if the thing that I'm searching for is less than the thing at the middle index, then I need to search left. Else if the thing I'm searching for is greater than the thing at the middle index, then I will need to search right. So how did I end up searching left? I ended up updating one of my index values. Which one? My right one. Right index is going to end up being the middle index minus 1. Right? And to search the right, I need to update my left index. It's going to end up being the middle index plus 1. Right? Yeah?
I have a question about your conditions for your else if statements. Why did you decide to do it the way you did instead of, how the key is greater than array?
Oh, I like to think of, okay, so first of all, do I even need this if right here? Do I need that? No, why? It's either equal, less than, or greater than, right? So I don't need this third check right here. I'm just doing it for illustrative purposes. Now you could have said instead something like key is greater than, like that. Mathematically that's exactly the same, but I have a hard time wrapping my idea of, well, which side is the key on? The key is either greater, it's over there, or it's lesser, it's over there. And so I end up, for demonstration purposes only, I end up doing it like this. I would actually get rid of that third condition entirely. Right? Okay? When I break out of this while loop, what has happened? You have not found the thing that you're looking for. The left index and the right index have now passed each other. The right index is greater than the left index, right? So now I'm doing two reversals. I have to reverse it for you, and then I've reversed it here, so I don't know which one I'm talking about anymore, right? In any case, this is an unsuccessful search. What should I return? What did we return last time? What index value indicates I didn't find it? -1, right? Or just any negative value, but -1 is best here. Okay. Let's go ahead and compile this. I'm still using the book stuff here, so demo.c. Oops, I misspelled left. The while, that left. There we go. Can't see anything. There we go. All right, so let's run this. Oh, by the way, the demonstration I'm running down here is, there's the original array, ARR, 1, 2, or 7, 1, 8, 6, dot, dot, dot. We've not yet talked about sorting here, so what I did is I sorted it manually. 1, 2, 3, 5, 6, 7, and then we had 2 8s in there. The thing that we're searching for is 42, so let's use binary search to search for 42, in which case we're not going to find it, right? And we're going to get -1. Let's redo it for something that we do know is correct. I don't know, let's search for 2. We're going to end up finding it at index 1. Let's search for one more thing. 8. Where's it going to find it? There are 8 things in there, by the way. So the last one is at index 7, and the other one is at index 6. Which ones is it going to find? I don't know. It looks like it found 6. It's not going to find one of them, or the first one, or the last one. It's just going to find unindex. And it entirely depends on how you implemented this binary search idea. Apparently it landed on this one first, and that's the one that it returned. If you want to find them all, that's a different problem, right? But you can still use binary search to do it. All right, now that we've seen binary search in action, we do not write our own, right? Just like we don't write our own lfind or sorting algorithms or anything like that. There is a function called, guess what? bsearch. What do you think the B is for? Binary search. And it takes a key, a pointer to it. Or sorry, that doesn't look right. That should be a pointer. I'm not sure why it's like that. It's not passed by reference. At least I don't think so. But in any case, it takes a key. Base is going to be the array that you are searching, the number of elements, the size of the array, and then finally the size of each element. For the same reason that we did it with linear search, lfind, right? It's completely generic. It doesn't know where the first thing is and where the next thing is and where the next thing is. You have to tell it, oh, each one of these things is 4 bytes. So the first one is 0 index offset, and then 4 bytes over you can find the second one, then the third one, then the fourth one. Well, if it's 8 bytes, then it needs to be told the first one is at the first 8 bytes, the second one is at the next 8 bytes, 8 bytes, 8 bytes. If it's a book and it's 40 bytes, it needs to be told 40 bytes, 40 bytes, 40 bytes. And then finally, a comparator that you are using for this, okay? So let's go ahead and rewrite this. I'm going to still use my sorted array up here and use bsearch instead. Another thing that's different here is that it does not return an index value. What does it return? A pointer to where it finds it. What if it's unsuccessful? What's the only pointer that indicates I didn't find it? Null, right? So let's go ahead and create a pointer here. Found. Did I already use found? I think I might have. There it is, found int. All right. So found int 2, I'll just say. I shouldn't do that. I'll just go with found. bsearch. Right? Now we need the key. The key right here is right there. And so I will pass it by reference, I believe. I don't think that man page was correct. We'll find out here in a second. And then what's the next one? There's the key, the array that you're searching for, the number of elements in there. So the array, sorted array. The number of elements in it is 8, right? And then how big is each element if it's an integer? Size of int, right? Don't just hard code that to 4, right? And then finally the comparator that you want to use to search it. Well, if it's in ascending order, then we need a comparator that compares integers in ascending order. If we used a comparator that reversed that, it would not find it. Why? Because it goes searching for something that is greater, but then it's out of order. It's in reverse order. So it goes in the wrong direction. So let's go ahead and use this correct one down here. Compare int. All right? The key that I'm searching for is 8 here, so printf found %d at memory address %p, %p and the line. And so found and then found. All I'm doing there is dereferencing it so that I can see what's stored there, and then the actual memory address. Now this is a successful search, so this is safe, right? I found 8 at memory address whatever, whatever, whatever. Let's search for 2. We're going to find that at some other memory address, whatever, 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 right? What if I searched for 42 though? What is it going to return? Null, right? Because there is no 42 in here. So what's it going to end up returning as the pointer? Null. What happens when I dereference a null pointer? Bret Hart says segmentation fault, right? So I need an if condition just like we did for this find up here, right? If found is not equal to null, then it's a successful search and we can do something like this. Else printf not found, right? There. That's much safer. There. Now it's not found. And we can go on with our lives. Unsuccessful search. Okay? So, I did this manually by just cutting and pasting it and sorting it. Well, there's this other sorting algorithm, in fact, this whole world of sorting algorithms that we're going to spend the rest of the week on, but we're going to start first by looking at the correct way of doing it. By the way, bsearch is where? In the standard library. We've got this other thing called qsort. We'll talk about what the Q stands for later on, but what do you think it does? It sorts. How does it sort? I don't know. Who cares, right? It does what it says in the tin. How does the square root function work? Who cares? It just does, right? This qsort will actually change your array. Whereas before the array was constant, right? Let's take a look over here. There's the base, there's the array, and guess what? It's constant. That's telling you that it's not going to be making changes to your array. This is not constant. What is that telling you? It is going to be making changes to your array. It's going to be rearranging stuff, right? And otherwise it follows the exact same pattern. Here's the array that you want to sort. There's the number of elements in the array. There's the number of bytes in each element. And then here's the comparator that you want to use. Right? So let me come back over here and change this so that I'm not using a sorted array anymore. In fact, let's undo that. I'll keep it in the code here. But instead, let's sort it first. First, sort the original array. Right? The original array up here was ARR. Right? It's unsorted. So let's sort it by calling qsort. By the way, is there any return value? Did you see a return value? No. Why? What is it doing? You give it an array, it mucks with it, rearranges it, and then returns. Right? It changes the thing that you give it. Okay? So qsort, what are the arguments here? In fact, there they are. Right? There's the array that you want to sort, but I'm not using a sorted array anymore. I'm using ARR. The size of it, the size of each element in it, and the comparator that you want to use. Right? Before we actually do all that searching stuff, let's actually make sure that it's correct. For int I equals 0, I is less than 8, I plus plus. Right? Printf %d, comma, array sub I. There. Beforehand, I'll say printf ARR is equal to, and afterwards, I'll say print ARR is equal to, or the end of the array, and then an end line there. Right? I'm going to prove to you that it's actually sorting. In fact, the rest of that stuff we can keep. Right? Oops, not sorted array anymore. What is it? ARR, ARR, and that's it. ARR. Okay, good. There. There it is. I did not have to manually sort it, right, by rewriting it. Instead, I used qsort The Q, by the way, stands for quick. I quick sorted it, and it gave me 1, 2, 3, 5, 6, 7, 8, 8. And all of these other values or all of these other searching were working. Right? Let me show you what happens if you don't sort it. So it's going to remain the exact same way, but what happens when we say search for 2? Let's find out. Remember, 2 is in there, right? Did it find it? Nope. That one didn't find it. This one got lucky and did find it. Why? Well, this is just a different implementation. It just got lucky somehow. What about searching for 8? Oh, that one got lucky too. I don't know. What's the actual? Let's go with 7. 7, they should both fail. 7. And then let's recompile and run. There we go. 7 didn't find it with my implementation, and bsearch did not find it. But it was in there, wasn't it? In fact, it's right there. It's at the first element. Again, why do either one of these binary searches work? It's not sorted. So it'll end up looking at, say, this one, say 6. Oh, the thing I'm searching for is greater than that. So where does it end up searching? In this half of the array, but it's not sorted. 7's not there. It's over on the wrong side. Only sorting it makes binary search work. Okay? So that's how you do it in C. In Java, really quick here as a review, because I did it last time not knowing that there was no linear search, so it was just binary search, right? Well, how did we end up doing this? Well, we load up the books. There's my book key, collections.sort. Right? It'll sort anything that you give it, as long as you give it a comparator to sort it by. Right? Now, the way to look at this, all this stuff, is let's go to, where's my iDrive? There we go. Comparator diagram. Nope. This is the one I want. The way to look at all of these things is this really generic algorithm, right? There's the black box right there, right? What is that sorting algorithm? I don't know. I don't care, right? Just like square root. How does it work? Does it use an interpolation method? Does it use a Taylor series? Does it use whatever? Who cares, right? It's just a black box. You give it input and you get output. But if you're going to use this one black box to sort anything, to sort integers, to sort doubles, to sort books, you need to give it something else, a comparator. Because when it looks at these two things, it doesn't know that they're books, it doesn't know that they're integers, it just knows, are they out of order, in which case I need to swap them, or they're in order, in which case I need to leave them alone. That question is handed off to the comparator. A, B, what are they? Are they books? Are they integers? I don't know. The comparator knows. Right? And so the comparator is able to say, well, those two things are in order, or they're out of order, or they're equal. So if they're out of order, what do I need to do? Now I'm the sorting algorithm. If they're out of order, what do I need to do? I need to swap them to put them in order. Right? The same thing works over here in Java. All we're doing is saying sort this array of books, or this list of books, I should say, using this comparator right here. Compare book by title. Then you can use binary search, passing in the array that is now sorted, the key, and the same comparator that you used. If you sort it by, say, authors, and then you search by title, are you going to find what you're looking for? Probably not, right? Or if you do, you're just getting lucky, right? So you need to make sure that you are using the correct comparator. If you sort it one way, you have to search the same way. If you sort it a different way, then you cannot search by a different way, like by title, then by date. Right, there we go. I'm not even sure that this will work. There we go. Because other is null. Yeah. I don't think I'd end up doing the dates anyway, did I? Oh well, that's okay. All right. Oh yeah, that's because my key doesn't have a date, does it? I set it equal to null. So I'd actually have to set the date of Dune here to 1965 or whenever it was released, right? But if I search, if I'm consistent about it and I search by title, then it will work. All right. Here's found Dune right there, Frank Herbert, and there they all are in order. What's the order? Author, then date. So Arl, Gibson, Heinlein, Herbert. It's in order according to the author. But what about? And I'm not printing any of these things, but what about all Frank's books? They are in fact in chronological order. Right? All of Terry Pratchett's books are in order. Color of Magic was definitely his first one. Raising Steam was one of his last ones before he died. And Name of the Wind came first, then Wise Man's Fear. And anybody read either one of those? So everybody knows about Game of Thrones, and the last book has been like 20 years since he promised it, or something like that. That's another series that he promised a trilogy, and he's not yet produced. In fact, he did wasn't it a fundraiser? He did a fundraiser saying, if we raise enough funds for this thing over here, I'll release a chapter that I've got it completed. They raised enough funds, and he never released the chapter. So it's not that great anyway. Nobody who's read it? Patrick Rothfuss? No? Okay, fine. All right, so there is searching and sorting the right way in C and Java. Right? Now my question for the rest of the week is going to be, how does this work? Right? How does QSort work? Okay. To motivate that, let's think about how we might sort as humans first. Okay. So let's go ahead and take a look at just an unsorted array here. Right. You tell me. I'll take the original array that we had over there. What was it? 718, 6, 2, 5, 8, 3. Right. Now I'll switch over here. All right. Just as a regular old human, sort this for me. What would you do? Go ahead.
So what I would do is I'd look around for the lowest value.
Okay.
First, and then I'd put farthest left and look in the
Find the minimum. All right, which is going to be what? 1. How did you know that was the minimum? You're a human. There's only 8 things there. You saw it immediately. A computer doesn't have that luxury, right? So how would you go about programming a computer, dumb machine, to find the minimum? I would start here, 7. Right? Then I would look at the next one. Is that less than what I've found so far? Yep, so there's my minimum. Then I would still have to go through the rest of these things to find out that 1 is in fact the minimum. Right? So in other words, I would have to look at everything, making how many comparisons? 8 comparisons to find the minimum. That's how many things are in there. Right? Now, once you've found the minimum, what do you do?
Once I find the minimum, I look for the next smallest value.
Okay, well, should we leave 1 there? I should ask. I think you said it at the end. What would you do with 1?
Oh, I'd put farthest left.
Okay, so swap the minimum and the first element. Okay, so what's that going to look like? Swap those 2. All right, and we're left with 1, 7, 8, 6, 2, 5, 8, 3. There we go. I could use technology. There. I didn't have to do that. There we go. So 1, 7, 8, 6, 2, 5, 8, 3. It's an 8. Oops. Yeah, that's an 8. There you go. All right, now you said to go through and find the next value, the next minimum. But do I bother starting it here anymore? No, that's where it needs to be. It's sorted. Right? So among the remaining elements, I'm going to find the next minimum. In other words, I'm going to repeat this step and then this step, but not the first element. I'm going to swap it at the second element. By the way, what is the next minimum? 2, right? How many comparisons would you end up having to make to find that? 1, 2, 3, 4, 5, 6, 7. Or you don't make any comparisons with the first one, so it's technically 6. And this one up here was technically 7 comparisons. So technically it's only 7. Why? Because you don't compare the first one with itself. Okay? Then what would you end up doing? 1, 2. Once you swap these two, then what? 8, 6, 7, 5, 8, 3. Let's fast forward a little bit. And at the same time, let's think about this more inductively and more abstractly. Suppose that I'm on the ith iteration, okay, of this idea. Okay? That means I've got a section of the array that is sorted. Index values 0 through I minus 1. I'm looking at the ith value, ith plus 1th, dot, 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 up to n minus 1 here. And this is unsorted. Okay? So now think about how to find the minimum among these guys right here. Right? Let's just write some pseudocode off to the side. How do I find the minimum between those, among all those elements? Let's create an index, first of all. Where do I start it? Find min. Or index of min. Right? Where do I start it if I'm just searching this part of the array? At I. Okay? Now, I need to go through the rest of these elements right here. So, for j, because I've already used I, right? Can't use it again. Starting where? I plus 1 up to and including n minus 1. In other words, I'm going to go look at this guy, dot, 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 this guy. If I ever find something that is less than the minimum that I've found so far, right? In fact, let me rename this to min index, or index of min, whichever one you want, right? If the array sub j is less than the array of min index, capital I, then I've found something less. So what do I do? Min index is equal to, help me out. I? No. I is fixed. Am I ever changing it? No. So what should I update it to? J. Right? J is running I plus 1, I plus 2, dot, 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 all the way to the end here. I want to find the minimum index. Once I've found it, what do I do? Swap. Which ones? Well, the minimum, definitely, min index. And so if I found the minimum element right here, where does it go? Remember, it's among these elements right here. So does it go over here somewhere? Nope. This is sorted. Never touch it again. So where does it belong? M right here. Where does it belong? Right here at the beginning. So array sub I. There. How many times do we do this? In other words, I'm going to package this up into a subroutine because it's just the ith iteration. What should I run I from? Well, where did we start it over here? We started at the very beginning, right? 0. Dot, dot, dot. Up to what? Let's fast forward on this one. The very last iteration, what should it look like? 1, 2, 3, 5, 6, 7, 8. And this is sorted. And then there's this other 8 over here. Do I need to sort an array of size 1? Nope. What would I end up doing? Oh, 8 is the minimum. Okay, swap it with itself. Oops, I didn't want that. Swap it with itself. Right? Is that worthwhile to do? No. So I'm going to stop this short at n minus 2. Right? All of this together is called selection sort. Right? And it's a very common sorting algorithm to teach as the first sorting algorithm. Why? Because it's how we would sort as humans. Right? Unfortunately, it is extremely slow, and I'll demonstrate that on Wednesday and why we don't use it. Right? But that's the idea. We'll implement it on Wednesday and see why we don't like it. Right? All right. See you next time.